So far what we have done is we have discussed the electrostatic fields, the basics of electrostatic field solutions. We are now going to develop the finite elements method and apply it to electric field solutions. Now, before we go on to the finite elements method, there are certain preliminary things that we need to study, and that is what we are going to do today. We have already started with the standard discrete systems, which tells us that when we are going to employ a numerical technique, what we need to do is we need to discretize our domain, solution domain, and there are certain rules and principles which we need to follow in order to apply, in order to deal with the continuum as a standard discrete system and obtain its solution. Today, I'm going to start with something called weighted residual methods. Let me come to that. I'll come later to what I mean by the Galerkin's method of weighted residual. First, let me talk about certain preliminary things. Now, we are going to look at the finite elements method. As we have already discussed, the finite element method, you will find more books on structural engineering, on mechanical engineering, rather than what you will find about the application of the finite elements method to electromagnetics. This is because the finite elements method was originally evolved in the computation of structural analysis problem. And then when people realized that this technique could easily be incorporated into electromagnetics, we started using them for electromagnetic problems. And this is not a very recent thing. We've been doing this since the 1960s. And nowadays, it is applied to diverse research areas. You can apply them to machines, waveguides, semiconductor devices, and so on and so forth. The reason is that it's a very powerful and versatile method. It can effectively handle problems, including complex geometries. It can handle inhomogeneous media. And the most important thing is, in this course, what you're going to do is you're going to develop in MATLAB a finite element program. And firstly, you will deal with electrostatic problems. And later, I will show you how you can make incorporate small modifications, or sometimes not so small modifications, and you can utilize them for other fields like electromagnetic fields, etc. In fact, those of you who are from mechanical engineering, you also already know that you can apply it to various problems of non-electrical nature. So that is what we are moving towards. In the first assignment that you will have at the end of this lecture, you will write a finite element code dealing with electrostatic problems, but we will we'll talk about that later. Let us go forth. So if you remember, in the standard discrete systems, what we discussed is that we need to take the whole and we need to break it up into pieces. For circuits, what we did was we took the entire circuit and broke it up into branches, and we set up equations which govern the behavior of each single branch. Now, we would like to do the same when we are working with the finite elements method. Now, if you remember, in the finite elements method, what we have to do is we have to solve a partial differential equation. And the first thing that we have done after we have identified the partial differential equation is we need to identify the solution region. So what is the solution region that you need to find the electric field in? And take that solution region and divide it into small domains. This process of discretizing the solution region into small domains, these domains are the elements. This process is called meshing. And then we take each element at a time And just as we have done for each branch in this electrical circuit, we set up a governing equation for a typical element, for a single element. Then, following the rules of the standard discrete systems, we must assemble all the elements into a solution region. Once we have done that, if you remember, we used KCL in case of circuit analysis. So we set up a voltage current relationship for every branch in the circuit. And after that, we applied an additional rule, the additional rule of KCL at a node. And at every node, we were able to establish an equation which had contributions from more than one element. So that was the governing principle of assembling the elements in the solution region. Once we have, following whatever rules we have in hand, once we have established this global matrix, global equation, we can solve this equation to obtain a global solution. So the solution analysis is for the global matrix, so the global equation. Whereas individually, we first have to set up individual equations, and only then we can go on to the global equation. The global equation must, of course, be solved subject to boundary conditions, because as you know, only when you solve subject to boundary conditions for a specified set of boundary conditions would you be able to obtain the unique solution to the Laplace's or Poisson's equation. So when we are talking about discretization of space, first we will have to figure out whether we are working in one-dimensional or two-dimensional or three-dimensional space. We will talk about this later. How do we decide which dimension we would like to work in? But depending upon the dimension that you work in, your elements will also be of that particular dimension. So if you're working with a linear problem which has a variation, let's say only in X, you might be working with an element like this, a linear element. Each element is bounded by two nodes. So this is a linear two-noded element. It's a one-dimensional element. This is a two-dimensional element. The triangular element is the simplest two-dimensional element that you can think about. You have a variation in the X domain, you have a variation in the Y direction. So this is a three-noded triangle. You can have a four-noded quadrilateral. You can have even a quadrilateral, which is a two-dimensional quadrilateral. However, it can have more than more than four nodes. So it does not only have nodes at the vertices, it is also possible to have nodes elsewhere. But of course, that will come later. We will discuss this later. A three-dimensional problem, again, you take a cube and you have elements only on the vertices. It's also possible not to have elements not just at the vertices, but elsewhere, but we will come to that later. Right now, we are going to concentrate on the one-dimensional problem. So we will talk about only the two-noded linear elements. So this is about discretization of the space only. So now what we are going to do is we are going to talk about weighted residuals. Now let us imagine I have a differential equation, which you see here on the slide, d2u dx squared minus u is equal to minus x. And this is defined over the domain 0 to 1. I need a set of boundary conditions. This is a one-dimensional problem. So I need two boundary conditions at the two boundaries of my solution region. Let's say u at x equal to 0 is 0 and u at x equal to 1 is equal to 0. So at the two ends, the value of u is 0 and there is some variation between the two. Now, I do not know the solution to this problem. Now, of course, I can find an exact solution to this problem, but we are not going to do that. We are going to see if we can use a numerical technique. So we are going to desist from finding the exact solution. Now, if you're going to use a numerical technique, there will be some approximation. You are not going to be able to find the exact solutions. Let us assume a trial function. Let us arbitrarily assume that the solution to this equation is u tilde. The reason I use u tilde instead of u, the solution would be u equal to something. The reason I use u tilde is to differentiate it from the exact solution. So u tilde would be an approximate solution obtained by some numerical technique, and it will be different from the exact solution, which will be specified as u. Let us imagine that a priori, I know the nature of the solution. So I assume that u tilde is equal to ax 1 minus x. Now, if you look at the solution, there is an unknown coefficient, and this unknown coefficient a will need to be determined. How will I determine this? If I assume, I'm allowed to assume the nature of the solution because I have already accepted the fact that I am looking for an approximate solution. I'm not looking for the exact solution. So if the chances are that if I choose an intelligently guessed approximate solution, I will have some error and I should be able to estimate this error. Maybe that error can be low, maybe that error can be high. We'll talk about that later. But I can accept that this is a solution to the problem. Now, if I need to, I don't know why this hand is coming. What is this about? I must have enabled something. Okay, never mind. So if I need to find A, I have to take the help of my boundary conditions. The trial function must satisfy the boundary conditions. I have only one unknown, therefore one boundary condition is sufficient. Of course, if I choose a solution which is very different from the actual nature of the exact solution, my error will be quite high. So I need to firstly intelligently choose a trial solution. Right now, I'm not going to talk about how to choose the trial solution, but we do understand that the accuracy of my approximate solution, so the error between my exact solution and my trial solution, will largely depends upon the choice that I make of a trial solution. So suppose the nature of this is exponential, nature of the solution of u for this equation, let us imagine it's exponential, and I choose a solution of this nature. So no matter what value of a I choose, I'm not going to be very close to an exact solution. We do understand that, but it is possible to obtain an approximate solution. Of course, I would like my solution to be as accurate as possible. Even given this particular nature, I would like this solution to be as accurate as possible. The accuracy will depend upon the trial's function, true, but secondly, there must be some way to reduce the inaccuracy. And that is where my concept of residual comes in. What is the residual? The residual is defined by the value of the left-hand side, not the left-hand side. Let us take this and the entire equation. I take it all the terms to the left-hand side and leave only 0. So this equation becomes d2u dx squared minus u plus x is equal to 0. So u, the exact solution, satisfies this equation. We understand that the trial function u tilde does not satisfy this equation exactly, and therefore if I put u tilde in this equation with all the terms on the left hand side, I am not going to end up with 0 on the right hand side. There will be a non-zero value on the right hand side, and this is called the residual. So the residual is calculated by substituting the trial function into the differential equation. So r is equal to d2 u tilde dx squared minus u tilde, this is a typo here, this should be u tilde, plus x. If u tilde is equal to u, this entire thing becomes equal to 0. However, this will not become equal to 0 if I take an approximate solution. I can evaluate this solution. I have already U tilde, I've already assumed U tilde. So therefore the residual can be estimated as minus 2a minus ax 1 minus x plus x. So I have an expression for the residual. And this expression for the residual involves x. It also involves the coefficient a. Remember, this coefficient a, I still have not obtained. I will obtain it subject to the boundary conditions. So what would you like to do? You would like to make this residual go to 0. If the residual is 0, it means that your U tilde is very close to the exact solution U, and that is exactly what you would want. You would want the approximate solution to be equal to the exact solution. So what you would like to do is you would like to minimize the residual. So my problem reduces to one of determining the constant a such that the trial function best approximates the exact solution. Am I clear so far? If you have any questions, please ask me now before I go further. Everybody?
It's clear to me.
Yes?
Ma'am, it's clear to me.
Okay, good. Now, one way to do that would be to make r equal to 0 at every value of x equal to 0. So no matter what value of x I choose over the entire region from 0 to 1, r should ideally be equal to 0. But that may be a very tall proposition considering the value of a. I mean, I just need to choose a value of a, and I want that by choosing this value of a, r will be 0 at every value of x, that is over the entire region. It is unlikely to happen. So I will kind of try to do something that I feel is easier to do and more likely, and that is I am not going to make r equal to 0, but I am going to make the weighted average of the residual over the problem domain equal to 0. What does it mean? I want to take the weighted average of the residual. So residual is to be weighted by a factor w. How do I choose w? I'm coming to later. By some means, I'm going to choose a weight function w, and I'm going to weight the residual with this w. So I have WR. And then I am going to take the weighted average of this function over the entire problem domain, which means 0 to 1 WR dx. So I am weighting the residual at every point. So let's say I have, let me try and, let's say this is my weight, this is my function, this is my residual, and x goes from 0 to 1. What I'm going to do is for every point that I have on this curve, I'm going to weight r. Let us say this is not the function, but the residual, that is difference of the function from the exact function. So let's say this is r, and every point in r is going to be weighted by a weight function w. Having done that, I am going to try and take the weighted average of this residual, and I am going to make this integral come to 0. This is what I want to do.
We want to do that because we want to decrease the number of computations.
No, let me come to that. I'll discuss this. So what we are trying to do is, we are not trying to make the residual go to 0 at every point, but we are kind of trying to make the average residual go to 0, or we are kind of trying to reduce the average error. I'll come to the consequence of that later.
Ma'am, we could have directly reduced the R why we are weighing it like multiplying by W then
Yes,
again parent derivative.
I'm trying to find the, yeah. Okay, look at this problem. Don't look at the discussions. This is the curve that you have seen before. Let's say this red curve is your solution. This is your exact solution. And what you would like to do is you would like to use an approximate solution. Okay, let me not use this curve. Let me try and draw this. Let's say this is the curve. This is your XY axis, very badly drawn. And let us imagine this curve, I do not know the nature. So what I do is, I say, I'm just going to approximate this with a linear curve. So I know the endpoints, I make the endpoints match, and in between, I just take an arbitrary linear function, okay? If I do this, there is an error. What is the error? This is your error. This is your error at this point. This is your error at this point. This is your error at this point. Some of it is positive, some of it is negative. Now, what would you like to do? You would like to have this green curve impinge on the red curve, or rather the red curve impinge on the green curve and match exactly, which means that this region has to be reduced. This entire region has to be reduced. This entire region has to be reduced. So in order to do that, what you would have to do is you would have to make R go to 0 at every point. Now, what we are saying is that this may be difficult for you to do. You will see later why it is difficult for you to do. But imagine you have a large number of points. Basically, you have an infinite number of points. And what you're trying to say is that at this infinite number of points, R has to be made to go to 0. This is going to be difficult, and you would like to make your life easier. So you hit upon this idea that instead of trying to make this go to 0 at every point, you would just like the average area, the net area, go to 0, so that the average error is reduced. So maybe you might have a big difference at this point, but so maybe a acceptable solution will be something like this. So what I'm saying is maybe at a particular point, again, I'm drawing very badly, maybe at a particular point, the residual is very high. But even then, doesn't this a priori look like a better solution to you? In the sense that overall, the deviation from the exact solution is less, even though at some point the deviation is high. So we are trying to look at a solution which is acceptable over the entire solution regime rather than at a particular point. We are looking at so it's like looking at a class average. I don't want a situation where one student does very well and one student does very badly. I would rather like all the students to do fairly well. So that is a more acceptable solution. So even in this case, the more acceptable solution is that I don't care if at 1 or 2 points the deviation is large, but overall the deviation of the approximate solution from the approximate solution from the exact solution should be as small as possible. So this is the approach that I'm trying to take. And therefore, instead of trying to make R go to 0 at every possible point, what I would like to do is I would like to make this I, which is equal to integration of WR dx from 0 to 1, go to 0. Okay? Does it make sense to you now?
Yes, ma'am.
Yes, ma'am.
Okay. So if I want to do that, I have a trial solution, so I can find the value. W is, so what I do is I take W. I'm not saying anything about W at the moment. W is, yeah.
Ma'am, actually, there was a question like why we are multiplying, means why
Are we weighting the function at all? Why just not work with the function? Yes, I'll come to that later. Give me a little time. For the moment, just accept this and let's see where we go. Right now, I'm not saying anything about W. So what you have to do is integrate 0 to 1 W d2u tilde dx square minus u tilde plus x dx, which comes out to be, which we have already evaluated, d2u dx square. This comes out to be W minus 2a to minus ax 1 minus x, etc. equal to 0. This you can always obtain. This is very easy. Now, you need to choose W. And there are various methods for selecting the weighting function. And depending upon the manner in which you select the weighting function, there are the method decides how you choose it. There are the collocation method, there's the least squares method, Galerkin's method. At least the least squares method, I'm sure most of you are kind of familiar with, in the sense that we choose in the least square method, what we try to do is, when we have arbitrary data, and we try to fit a function, we try to make the fit as close as possible. And for that, what we do is we try to minimize the mean square value. The least mean square value is tried to be minimized. That's a different method. In this method, we are going to use the Galerkin's method. And in the Galerkin's method, the weighted function is obtained from the chosen function. How? We choose W to be du tilde dA. U tilde you have already chosen. Again, this is completely arbitrary. Of course, there is a mathematical proof behind the Galerkin's method, but I'm not going to go there here in this course. Let us just use the concept that in the Galerkin's method, W is chosen to be du dA. So therefore, W becomes equal to x1 minus x. Now you can put this value here, and you can easily evaluate the integral and make the integral go to 0. If you make the integral go to 0, you will land up with a value of a, and the value of a that you obtain here, if you work this out, which I'm not going to do for you, is 0.2272. So therefore, your acceptable trial solution, u tilde, comes out to be, after incorporating the boundary conditions, comes out to be u tilde equal to 0.2272 x1 minus x. Now, this is an approximate solution, and of course, there will be error. Now, that is why in this particular case, I started with a solution, started with an equation which has an exact solution. Now, if you evaluate this integral using the exact solution at x equal to 0.5, the exact solution comes out to be 0.0566. And instead, if you use this trial function, you get 0.0568. Is this acceptable? It's a fourth place of decimal. So probably for most problems, this is an acceptable solution. But of course, whether it's an acceptable solution depends completely upon the application of the problem. Where are you using it? What is the physical significance of the variation in the fourth place of decimal? We were not going there now. I'm just kind of showing you how we do it. I'm just introducing you to the concepts. So what I have shown you here, without answering some of your questions, is that in the Galerkin's method of weighted residual, we obtain the residual, we weight the residual with a function. This weighting function for Galerkin's method is chosen by taking du dA. And after that, we try to make the weighted average of the residual over the problem domain go to 0. By imposing this constraint, we are able to find a solution for the trial function. We are able to find a trial function. And for this particular case, it does seem to be an acceptable trial solution. Is that okay? Any questions?
Ma'am, so by doing this, we can suppose we have chosen a trial function multiplied with a constant a. So by all these procedures, we can only modify a. We cannot modify this function, right?
Right.
Yes.
You are starting with a trial solution. Now, how you're coming to the trial solution, I'm not discussing at the moment.
Yes, ma'am.
If you choose a very, very wrong trial solution, no matter what value of a you choose, you're not going to go there. You can kind of reduce the error, but you will still have quite a bit of error.
Yes, ma'am.
going to introduce some more concepts before I start applying this wherever. We have discussed the concept of the method of weighted residual. Now I'm going to come to something called weak formulation. What do I mean by weak formulation? Now, if you look at this equation that we started with, what was this equation that where is the equation? This is my equation, d2u dx square minus u. Which is the highest order term here? d2u dx square. So it's a second order equation. Now, if I work with the second order equation, which means I take the residual. So what I do is exactly what I have done here. I've retained the terms as they were in the equation, and I have multiplied it by the weighting function. So I have a term of the highest order term that I have is the first term. So this is a lower order term, this is a lower order term, this is my highest order term. And what is the highest order term that I have? The highest order term that I have is W. Forget about the nature of W at the moment. W d2u dx squared. And this is exactly the order that I had in my differential equation. If I'm going to work with this is called the strong formulation. The strong formulation of the weighted residual method requires evaluation of an integral that includes the highest order of the derivative term in this differential equation. The highest order of the derivative term in the differential equation is second order, and while computing the weighted residual, I'm still working with the second order term. If I do that, which I can, that is called the strong formulation. What it means is that if I need to evaluate this term, integration w d2u tilde dx squared, the integral has to have a non-zero finite value, which means it must be integrable at least twice. And the second order derivative d2u dx squared must not vanish. So this kind of puts a constraint on my trial function. Whether d2, whether u tilde will be differentiable twice depends entirely on your choice of the trial function u tilde. You're going to choose u tilde from wherever, we have not yet figured out how we are going to choose u tilde, but we said we will arbitrarily choose u tilde. And if I'm going to choose u tilde arbitrarily, I would like all the freedom that is possible to me. The moment I say that it has to be integrable twice, I am kind of putting a constraint on the trial function that I can choose. I have to choose a trial function in which the second order derivative does not vanish. I do not like so many constraints. I do not want to have to satisfy so many criteria. And therefore, I figure out a way of reducing the requirement for the trial function, at least in terms of differentiability. What do? I apply integration by parts to the strong formulation. I take this term. Now forget the u and the x for the moment. This will just be multiplied by w. So this you will have a term w u tilde, and you will have a term x w, and then you will also have this constant term, which will take care of the boundary conditions. Now what I do is, instead of trying to evaluate this first term d2u dx squared, I apply integration by parts. And therefore, I can reduce this to minus dw dx du dx. I will not keep on mentioning u tilde. In this course, we are going to deal with approximate solutions. So whenever I talk about u, I'm actually talking about the trial function. So I'm actually talking about u tilde. It may be specified as u tilde here, or it may not be. I'm not going to specify. When I'm speaking out, I'll just refer to it as u. So instead of having to evaluate d2u dx squared, this can be reduced to dw dx du dx, which means u now needs to be differentiable only once. And of course, w has to be differentiable with respect to x. So these two expressions are identical, except that in this case, I have applied integration by parts to reduce it to a form which requires me to be able to integrate u only once, and w also has to be differentiable. So this is my advantage. And this method is called the method of weak formulation. The weak formulation of the weighted residual method is brought about by applying the integration by parts to the highest order derivative and reducing the order of the derivative so that a second order derivative reduces by one order. If you have a higher order derivative, it will also reduce by at least one order. So I am reducing the constraints that are needed on my trial function. Here there is some discussion about symmetric matrix, etc. I will not discuss this now. I will discuss this later when when it becomes more intelligible to you. So is this concept of weak formulation clear to you? So we have discussed two concepts. We have discussed the method of weighted residuals, Galerkin's method of weighted residuals, and we have talked about the weak formulation of the weighted residual method. Are these two concepts amply clear to all of you? Sudhir?
Yes, ma'am.
Ashok?
Yes, ma'am. It's fine.
Okay, I'm going to go forward now. Now, before I apply, so you know that we are going to solve the electrostatic problem, but before I apply this to the electrostatic problem, let us look at some easier things. Look at this problem. This is the solution. The red curve is the solution. Let us imagine that this is the entire boundary of your problem. What you would like to do is you would like to find the function which exactly describes this red curve, which is a polynomial. You have no idea about the order of the polynomial. So how are you going to choose the trial function? You have no idea. In the previous example, I just gave you some trial function from somewhere, God knows where. Now I'm saying that I want to find this red curve, which is a solution to a problem. The problem is not defined. I mean, it is defined. I'm not talking about it. So I know that the exact solution is this red curve, and I want to find an approximate solution which is as close to this red curve as possible. I have to then first choose a trial function, and then only I will be able to apply the method of weighted residual. So how do I choose this trial function? What would you guys do? If I asked you to approximate this red curve, what would you naturally do? Balaji?
Yes, ma'am. So the AX plus B.
Come again?
I would use a linear trial function, which is AX
You would use
plus
a
B.
linear trial function. Why would you use the linear trial function?
Because that is the simplest of all.
That's the simplest of all. Yeah, okay. Everybody likes a straight line. So I could simply do this. No, I have to say what to draw. I could simply do this. And it gives me a large error. So a linear function is not going to be suitable.
Ma'am, we will select multiple nodes and
So we
will
would select, so we are going to do what we discussed
previously.
previously, that we don't have any idea about the function, and we would like to work with the linear function because a linear function is the easiest kind of function we can think of. But if I choose a linear function, my error might be quite large. And there is no way you can choose whatever A you want, which will kind of give you a very good solution. But what I can do is instead, what I can do is I can break this entire region from x equal to begin to x equal to end. I can break this up into small elements. And over every element, I can choose a linear straight line. So in the end, my solution will be not a straight line going from here to here, but a collection of straight lines. Which, if you look at this collection of yellow lines, does seem to be not too bad an approximation for the red curve. I'll come back to this later. So therefore, One thing that we discussed earlier is that the accuracy of my approximate solution depends on the chosen trial function. You choose a good trial function, you can land up somewhere very close to your exact solution. But for an unknown problem, how would you have any idea about what a good trial function might be? So assuming a proper trial function for an unknown exact solution is not easy. And then you have further problems. The domain may not be a simple straight line, a one-dimensional problem. The domain may be quite complicated. It may be a complicated region in 3 dimensions. The exact solution may have a large variation over the problem domain, in the sense that the exact solution does not have to be it does not have to be quadratic or linear. It can be a combination of many things. This is what happens with my computer. Whenever I wave my hands, the slides go running. Okay, so the exact solution may be quite complicated, and it may not even be possible to use one trial function to approximate the exact solution everywhere with the same trial function. And the problem might have complicated boundary conditions. You may not have any idea about the exact solution. Really and truly, you're going to use a numerical technique only in those situations where an exact solution is not possible or very difficult. So therefore, if I put the requirement that I must know my trial function, it's not going to make you very excited. So what I could do is I could use a piecewise linear function. This is a piecewise linear function that we talk about. So between this point and this point, instead of choosing a single linear function, I have chosen a piecewise linear function, in the sense that it is a collection of small pieces of straight lines. And visually also, you can figure out that this might be quite acceptable. What do we mean by a piecewise linear function? It means that I am going to choose a function like this. Let's say I call it wi. Don't get confused by the wi. Wi is just an arbitrary function which varies with x. So as I go over x, as x varies, wi varies. I have chosen, see, I'm going to work with discrete values. I'm not going to work with continuous values, which means that my straight line is no longer, as I go from x to 0, from 0 to 1, it is not comprised of an infinite number of continuous points, but it is comprised of discrete points. So I have chosen 3 points here, 3 points here in the x domain, xi minus 1, xi, and xi plus 1. There is some distance between the two. Let's say hi is the distance between xi minus 1 and xi, and hi plus 1 is the distance between xi and xi plus 1. Now, I am now choosing a particular function wi such that I'm giving you a function wix, which is equal to x minus xi minus 1 divided by hi in the region between xi and xi minus 1. And in the region between xi and xi plus 1, wix is equal to xi plus 1 minus x divided by hi plus 1. It is 0 otherwise. So this is how your wi looks like. It goes from xi minus 1 to xi. It goes, so beyond xi minus 1, it is 0. Beyond xi plus 1, it is 0. From xi minus 1, as I go to xi, it rises from 0 to 1. And again, as I go from xi to xi plus 1, it goes from 1 to 0 linearly. Okay, this is a function that I am giving to you. Let me also say that this is probably the trial function or somehow related to the trial function. We have only put the condition that it should be a linear function. So this is a condition that I'm choosing for w. Let's see what I do with this. Forget that for the moment. Now come back to our problem. In the entire domain, I'm going to break it up into small pieces. So instead of taking a collection of continuous points, I'm going to take a collection of discrete points. So here I have taken over the entire solution regime, wherever that is. I've not specified the values of xi because I'm talking conceptually at the moment. I have taken 1, 2, 3, 4, 5, 6, 7, 8 points. And these are, let's say, called nodes. So what I am doing by this is I am breaking up the entire solution domain into subdomain. And each of these subdomains are called finite elements. And instead of generalized coefficients, what I mean by general coefficients is instead of trying to decide an exact approximate solution U tilde over this entire regime, which is obtained in terms of generalized coefficients, that's what we did. U tilde was taken to be ax1 minus x. So a is your generalized coefficient. Instead of trying to do that, what we are going to do is we are going to use piecewise continuous functions, which are defined in terms of the nodal variables. So let's consider any two nodes. Let's say any two nodes are xi and xi minus 1. So this is x1, x2, x3, x4, etc. Let's take this one, or you take this one. In any case, the first node is xi and the next node is xi plus 1. This is a two-noded linear element. You do not know the values, but u, which is your solution, the function that you need to solve for, has a value ui at xi and ui minus 1 at xi plus 1. We don't know these values. Now, this is a two-noded linear element. So if you go back to the different kinds of finite elements that I talked about, this is the first kind of element, that is the two-noded linear element. Why we are saying that this is a linear element, I'll come to later. So I am going to use two-noded linear element, which is bounded. So I know the coordinates xi plus 1, and I know the values ui and ui plus 1. I know them only as I know them in terms of the variables. I don't have the values. And what I'm saying is that over this element, as I go from xi to xi plus 1, I should be able to obtain a trial solution for u, which is specified in terms of the nodal variables. What are the nodal variables? Ui and ui plus 1. So what am I saying? I am saying that I am at the moment just taking out one element. I've broken up into various elements. I'm just taking out one element. And I am concentrating on that one element. Remember, that's what we did with branches. Let's concentrate on one single branch of a circuit. Let's concentrate on one single element. And over this element, I am trying to find a solution function. What kind of solution function am I trying to find? The solution function should be such that it will only be defined over this element, which means it will only be defined from xi to xi plus 1. And this will be a continuous function which is to be specified in terms of ui and ui plus 1, which are the nodal variables. Can I do that? This is my problem. Just as in the circuit element, I have obtained an expression for voltage and current in terms of the nodal voltages only and the nodal currents only. Similarly, I would like to do this. Find a solution in terms of ui and ui plus 1 only. And I don't really want to bother about the rest of the solution, because as you can see, the solutions are different. The solution here is this straight line. The solution over the next element is this straight line. So for every element, I need to find a different solution. So I am concentrating on one single element and a single solution that is applicable only to that element. You would like to choose a linear function? So I'll do just that. I will define u as a function over xi. Sorry, I will choose a function ux as varying linearly from nodes xi to xi plus 1. So at node I can write, at node xi, I can write u as a function of xi only, which is c1 xi plus c2 is equal to ui. Ui is the nodal variable at node I. The coordinate is xi. U at xi can be written as c1 xi plus c2 if I choose a function c1x plus c2 as the trial function over element 1. Similarly, u at xi plus 1 is equal to c1 xi plus 1 plus c2 which is again equal to ui plus 1. Therefore, it is possible for me, I need to evaluate C1 and C2. And in terms of the values, nodal variables, I can find C1 and C2. So C1 becomes equal to ui plus 1 minus ui by xi plus 1 minus xi, and C2 becomes ui xi plus 1 minus ui plus 1 xi by xi plus 1 minus xi. Now this is equal to hi, and this is equal to hi plus 1. Let us also assume that all the h's are equal. I've taken all the nodes equal, so it is equal to hi or h. Now, what have I done? I have obtained the values of the coefficients. I have not actually obtained the numerical values, but I have been able to express C1 and C2 in terms of the nodal variables only. So in terms of the nodal variables U1 and Ui plus 1, I have obtained C1 and C2, and in terms of Xi. So if I know Ui plus 1, if I know Xi plus 1, I should be able to find the solution U equal to C1x plus C2 over the first element. Is this clear to everybody? Up to this much?
Yes, ma'am.
Yes, ma'am.
Okay. Now, this expression can therefore be written in this terms. U is equal to hix ui plus hi plus 1 x ui plus 1. So whatever I have in terms of x, I club it together in a capital H. So capital Hix is equal to xi plus 1 minus x by hi, and capital Hi plus 1 x is equal to x minus xi by hi. Okay. So if I have these two terms, hi and hi plus 1, my function u becomes h into u, h1 u1 plus h2 u2. So I am now able to express my solution function or trial function in terms of two functions h, which are dependent on only the coordinates of the nodes. So the nodal coordinates define these functions hi and hi plus 1. I call them shape functions. And these shape functions multiplied by the nodal variables gives me the solution u over the branch. Does this shape function hi look familiar to you in any way from what we have been discussing so far? Have we looked at this kind of a shape function very recently, or this kind of a function
it's-
very recently?
It's the average between 2 points.
No. What does this function look like? If I go from,
Differentiability function.
does it look like this? Is this the function? At node I, of course. Isn't wi and hi the same function?
Yes, ma'am.
So I kind of gave you this function initially, and look, this is what I have landed up with. Why have I landed up with this function? Because I have chosen a linear function over the element in terms of the nodes at the two ends of that element. And when I have evaluated the coefficients in terms of the nodal variables, I find that u can be expressed in terms of h and u being the nodal variables and hi being the weight function, which I had already defined for you. How does it look? The weight function h or w at xi is equal to unity. It is 0 at every other node. And as I go from that node to the next node, it goes from 1 to 0 linearly. It goes from 1 to 0 linearly. So over every element, I have a weight function. I have actually two weight functions. I have hi and I have hi plus 1. So if I am looking at hi, it is defined at node xi. And at node xi, hi has the value in unity. And over this element, as I go from xi to xi plus 1, hi will become 0, and it will go from 1 to 0 linearly. I'm not going to talk about what is happening beyond this element. Similarly, on this node, I have hi plus 1, which is again unity, and it will go to 0 as I go from ui plus 1 to ui. It will go linearly from 1 to 0. Is that agreed? So
Ma'am, do
this
we know the
W
value of
and one minute. This W or this H are the same functions, and I call them the weight functions, or I call them the shape functions. Right now, I'm calling it the shape function. Yes, Hitesh, please.
Ma'am, do we know the value of ui and ui plus 1? Because you told
No,
that these are
no,
unknown.
no. We don't. We don't know. But we are expressing it in terms of ui and ui plus 1. If we know, we will know.
Yes, ma'am.
If we know ui and ui plus 1, we will know u.
Yes, ma'am.
Right now, we don't know. Sorry about this. So this is what my shape function looks like. If I have an element which goes from xi to xi plus 1, I have, at every node, I have two shape functions. I am talking about linear shape functions, so I'm defining the concept of shape functions at the moment. So the shape functions look like this. At node xi, or let's say 1 and 2, h1 is unity. h1 goes to 0 as I go to node x2. Node 2, which is x2 or xi plus 1, and the variation from 1 to 0 as I traverse the element. The element is linear. So I'm traversing the element, and as I traverse the element, the shape function h1 goes linearly from 1 to 0. This is very important. On the other hand, you have h2x defined at node 2. H2x is unity at node 2, and it goes from 1 to 0 linearly as I go from node 2 to node 1. This is the definition of a linear shape function. So if I formally define a linear shape function, the shape function associated with node I has a unity value at node I and vanishes at all other nodes. The variation over the element is linear. This is the criterion for a linear shape function, which means hi at xi is equal to 1, hi at xj, where I is not equal to j, must be 0. There is one more condition which must be obvious from this figure. If this, let's say this is 1, let's say the hi, I mean the distance between xi and xi1 is 1. Now, if I'm at the midpoint, what would be the value of hi at this point? h1 at this point, what would be the value of h2 at this point?
0.5.
0.5. So we are going linearly. So therefore, as h1 linearly varies, linearly decreases, here the h2 is linearly increases. So I have this condition, I have this condition that the sum of all shape functions is unity. So at every point, except the nodes, the sum of the shape functions is unity. Let me choose a point here. I arbitrarily, let's say I choose a point. So let me choose an arbitrary point here. I do not know the value of h2, neither do I know the value of h1. But what I do know is that h1 and h2 will add up to unity. And that will be true over the entire element. So what I know is I know the values of h1 and h2 at the nodes, and I also know the nature or the contribution of every of h1 and h2 at every point on that element. Now you may understand why I'm calling it the shape function, but we will discuss. So you can imagine that the solution in the region xi and xi plus 1 over this element will be, the shape will be determined by h1 and h2 and x1 and x2. X1 and X2 are fixed. You don't have a choice. I mean, once you have chosen the element, there's nothing more you can do. Now, once you have chosen the element, the nature of the trial function over this element will be decided by the function H1 and H2. And therefore, H1 and H2 are called the shape functions. I'm going to continue with this discussion in the next class. So we are kind of stopping in the middle of a discussion. Let me recap for you what we have discussed. We have discussed the method of weighted residual, Galerkin's method of weighted residual. We have talked about weak formulation. We have started talking about discretization. And we have also said that what we would like to do is we would like to break up the entire domain into linear small elements. And over every of these elements, we would like to have an independent trial function. So we have not one single trial function, but various trial functions. So as many trial functions as there are a number of elements. Now we are concentrating on each element, and in each element we are finding a linear trial function, and that linear trial function will have something to do with what we call the shape functions and the nodal variables. So that linear shape function will be expressed in terms of the nodal variables ui and uj and the shape functions hi and hj. We have also discussed the nature of the shape functions. What we do with this, we will see in the next class. Any questions so far? I'm going to stop here now.
Ma'am, what is the meaning of global solution?
We will come to that.
Yes, ma'am.
Let's talk about elements now. Any more questions? Okay, so I'll stop here now.